Determine all values of c that satisfy the conclusion of the mean value theorem for the function f of x equals 1 over x on the interval -1 included to 1 included. The first thing to do is to determine whether the two conditions are met for the mean value theorem to apply. The first condition, the function f of x, which is 1 over x, has to be continuous on the closed interval given. F of x, which is 1 over x, is not continuous everywhere because it does have a denominator, and that denominator is not allowed to be a 0. So x can't be a 0 here. And it turns out that 0 is in the closed interval given, and therefore we cannot say that it's continuous on that interval given. We have to say it's not continuous on the closed interval. Closed interval means that it includes both endpoints indicated by square brackets on both ends. But the 0 is within there, and therefore we're not continuous, and condition 1 does not hold true. Therefore, automatically, the mean value theorem is not guaranteed. The second condition is the derivative of f of x. Before we do that, let's rewrite f of x as a negative exponent, so we can use the power rule. Bring down the power, subtract 1 from it. It can be rewritten by moving the negative exponent to the denominator to become the positive exponent. Once again, we have a denominator here, and the denominator, which is x squared, can't be a 0. Taking the square root of both sides tells us that x can't be a 0. We need the derivative to be continuous, which is also called differentiable, on the open interval. But the interval -1 to 1 includes the 0 in there, and we cannot be the 0, so we also are not continuous on the derivative called differentiable, not differentiable on the open interval. It's always the open interval for the derivative because the derivative does not exist at the endpoints. But it turns out we don't exist at the 0 either, which is in between, so we're not differentiable, and condition 2 also does not hold true. And therefore, the conclusion of the mean value theorem is not guaranteed, since we had one or both conditions didn't hold true. You have to have both of them hold true for the mean value theorem to apply. There can still be a result where the slope of the tangent line at some value c equals to the slope of the secant line connecting the endpoints, f of b minus f of a over b minus a. But because we don't have the conditions holding true, this is in question whether this will happen. I'll put a question mark above it, and c ends up in the open interval if there's any c at all. F prime of c can be evaluated on the left side by plugging c in to f prime of x. So that will give us -1 over c squared equals 2. We're on the interval of -1 to 1. A is the left endpoint, B is the right endpoint. So this would equal f of the right endpoint 1 minus f of the left endpoint -1 over the right endpoint 1 minus the left endpoint -1. F of 1 and f of -1 can be evaluated using f of x up here. So f of 1 is 1 over 1 minus f of -1, which is 1 over -1. And then all of this over 1 minus a -1, which is the same thing as 1 plus 1. 1 over 1 is 1, minus 1 over -1 is -1, over 1 plus 1, which is a 2. And 1 minus a -1 is the same thing as 1 plus 1, over the 2. 1 plus 1 is 2, over 2, so 1. So we have -1 over c squared equals to 1. We can multiply both sides by c squared, giving -1 equals c squared. So to solve for c, we can take the square root of both sides, and c will equal plus or minus the square root of -1. Because there's a negative under the root, this is not a real number. And therefore we have no solution for the c value here. And that's not a surprise because back up here, the mean value conclusion was questionable. It was not guaranteed because the conditions were not met. So no surprise that we actually did not find a value of C. And the result of this is the mean value theorem conclusion is not possible in this case because we didn't have the conditions met.